Thank you for that introduction. And let me start by thanking the organizers for inviting me. It's a great pleasure to be here. So I'm going to be talking about a body of work that I've been doing over the last 4 or 5 years, largely in collaboration with Sylvia Serfati, who was at NYU and is now at Sorbonne. Some of the more recent work is also joint with Elias Hess-Childs, who's a talented postdoc with me at CMU, who's applying for jobs this cycle, and Jiaoyang Wang, who's at UPenn. So maybe before I dive in, I should make a disclaimer, which is I'm a mathematician. I consider myself an analyst. Hopefully, I have kept the technical details to a minimum. Instead, I want to focus on telling you a story about some ideas I've been interested in and how there's an interplay between singularity of interaction between particles, temperature, which for me is noise, and rates of convergence, if you will. So to start us off, the microscopic model that I'm interested in is a system of n particles, which is described by an energy functional of the following form. The first term is the interaction energy associated to some potential g. Later, we'll see some concrete choices of it. The second term is associated to a confining potential v. For the purposes of this talk, you could just assume that v is, say, quadratic. This is, of course, to prevent particles from escaping off to infinity. You'll notice here that I have a 1 over n prefactor in front of this first term. This is the ubiquitous mean field scaling. And what this does is it ensures that both terms in this energy functional scale the same way. They scale like n, right? Because I have n choose terms and n choose 2 terms in the first guy, like this. And so I normalize by 1 over n. Also, the fact that I have this 1 over n prefactor means that the energy of each particle is the average of all the pairwise energies generated. You'll also notice that I'm excluding the case where I is equal to j in the summation, the interaction. This means that there's no self-interaction in this model. A particle doesn't generate a potential on itself. And that's important because if we consider interaction potentials which have a singularity, in math terms this would be along the diagonal, that would correspond to something infinite. So it has to be removed in order to make physical sense. And the final comment is that I'm considering all pairs I and j, excluding the self-interaction case. In other words, the interaction is long range. Each particle is interacting with every other particle in the system, as opposed to, say, some nearest neighbor, other short-range interaction. So we're interested in dynamics. And the general form of dynamics that's associated to this energy functional is second-order kinetic system of stochastic differential equations. So the first term is not complicated, or line's not complicated. It's just expressing the fact that the change in position is velocity. The second line right here is essentially Newton's second law, which is giving the form of the acceleration. X is position, v is velocity. And the I is denoting the label of each particle. And I'm assuming that my phase space is some domain, d-dimensional domain. It's either the whole space or, let's say, a box with periodic boundary conditions, in other words, the flat torus. And of course, velocities are in the whole space. In principle, you can consider more complicated geometries, like a closed Riemannian manifold or some boundary conditions, but let's not worry about that. There's several parameters in this system. There's m, which is the mass of each particle, which I assume to be identical for simplicity. Gamma is the coefficient of friction. These wi are just independent d-dimensional Wiener processes, Brownian motion. The parameter beta, which a priori may depend on n, and in fact that's the most interesting case, has the interpretation of inverse temperature. And the noise here is modeling thermal fluctuations in the system. I have this other parameter, m, which is a matrix d by d with real entries, which I'll take to be constant in time. And this choice of matrix encodes the type of dynamics, as we'll see in a moment. In the particular case, when m is minus the identity, this is the classical Langevin system or underdamped Langevin system. Many of you, not all of you, have seen before. Okay, so here's just a toy caricature. I normally give this talk in front of audiences that are mathematicians, pure, who don't necessarily know so much physics, so this is a trivial statement. For this audience is that particles are moving in space according to their velocities, which of course are changing because of the pairwise interactions between the forces. So I'm going to simplify the problem even more because that's what allows me to actually prove theorems in general. And we're going to consider the so-called overdamped limit when we just formally set the mass parameter to be equal to 0, in which case we can express, it's a small computation that you can do as I'm talking, that the velocity of each particle can be solely expressed in terms of the position and the noise, and our second order system reduces to a first order system right here. Okay, so as I said, we're going to focus on this case because it's better understood. And in this context, the choice of M corresponds, or we'll consider, primarily two different choices. The first is what I'll call Hamiltonian or conservative dynamics, which is when M is antisymmetric. And the second is what I'll call gradient or dissipative dynamics, where M is minus the identity. So what is this G, the interaction potential? In this talk, I'm interested, or we're interested, in this log or Riesz interactions, which will index by a parameter S, which I'm always assuming is strictly less than the dimension. Okay, so this family right here, S not equal to 0 is just standard power law Riesz potential that I think everybody here knows. The case S equals 0 is limiting endpoint case. It's not a hard computation that if you take absolute value x to the minus s, normalize it properly, and let s go to 0, you will recover exactly minus log x in the limit as s goes to 0. There is a particularly important value of s, which is when it's d minus 2. This is the Coulomb potential that we know and love from electrostatics. And based on this threshold, we'll classify the strength of the interaction as being sub-Coulomb. So the singularity at the origin is milder than that of the Coulomb potential if s is strictly less than d minus 2. And we'll call the interaction super Coulomb if s is strictly greater than d minus 2. The singularity at the origin is stronger, but of course it also has faster decay at infinity. And we'll call such systems Coulomb or Riesz gases. So in this talk, we'll focus on the singular case where s is always greater than or equal to 0. The case s strictly less than 0 is also of interest, particularly in ML and stats context, but not maybe so interesting for physical reasons outside of dimension 1. We're also restricting to the potential case when s is strictly less than d. This corresponds to when this function g is actually locally integrable. Okay, if s is greater than or equal to d, it's hypersingular. This is also an interesting regime, but the expected limiting behavior is completely different. It is not a mean field regime. It's also more complicated. I guess it's what you would call a local density regime. And the other comment is that these interactions are repulsive, meaning that the energy diverges to positive infinity as the distance between particles tends to 0. And this is good because it actually prevents collisions between the particles. It's a small exercise to show that. So I'm not really here to talk about the applications because I'm not expert on that. But I'll just mention that there are numerous applications and connections to particle systems in physics that is obvious from the role of the Coulomb potential. These also play a role in particle methods for PDE, finding equilibria in interaction energies, biological, sociological models, large neural networks, random matrix theory, approximation theory, so on and so on. There have been a number of nice surveys that have been written over the years that go into more detail on these applications. They have lots of nice references. In the specific case of Coulomb and Riesz interactions, there's a nice survey by Matthew Levin from 3 years ago, and then from last year, a very comprehensive set of lecture notes by Sylvia that I recommend. So what are we actually interested in? We're interested in the behavior of this microscopic system when n is very large. And thinking of a gas in finite volume, recalling Avogadro's number from chemistry, very apt for this audience, that n is, say, of the order 10 to the 23, which is huge. In theory, you could solve this system of equations directly And in fact, if beta is equal to infinity, we're at 0 temperature, the dynamics are completely deterministic, and you know the exact behavior of every particle in the system. In practice, this is too expensive, if at all feasible, given the size of n, the nonlinearity, the coupling of the system, so on and so on. The punchline is that there's too much information in the n-particle system to do anything useful with it, and instead, we can adopt a statistical point of view and ask what are the approximate dynamics of each particle of a single or finite fixed number of particles in the system, and study that question. This leads us to the mean field limit, which we've already heard at this workshop and Keith's talk, and maybe you talked a bit about it in the tutorials that came before. More precisely, the question in math terms is what are the limiting dynamics of this object right here, the empirical measure, associated to the n-particle system. So I take my solution. At each point, I place a Dirac mass, I sum, and I normalize it. So that gives me a genuine probability measure on my phase space, the spatial part of it. And when I ask, what is the limiting behavior of this as the number of particles is very large? It tends to infinity. Well, it's not too hard to arrive at a guess. Just take a test function, test this against the empirical measure, differentiate in time. And then what this leads you to formally expect is that, well, if you have a sequence of initial point configurations whose initial empirical measures have some limit, which is nice enough, then their time-evolved empirical measures converges to a solution of this partial differential equation right here, which we'll call the mean field equation. So this term on the right-hand side is coming from the noise. It gets averaged out and just becomes diffusion. This term on the left-hand side is coming from the interaction. The grad V is from the confinement. And then this guy right here is from the pairwise interactions between particles. This is a nonlinear PDE. It's quadratic, has a quadratic nonlinearity. And this is coming from the fact that we assume we have pairwise interactions. If you had higher order interactions in your system, you would have a higher order nonlinearity. And in fact, another exercise is that when beta is equal to infinity, so that this noise term vanishes, you can check that this empirical measure is in fact a weak solution to this mean field equation. Okay? So terminology, establishing the mean field limit, refers to proving this convergence of the empirical measures to a solution of this mean field PDE. There's a closely related question, which is that of propagation of chaos. Now, suppose our initial positions are randomly distributed in a, say, IID fashion, independent identically distributed, according to some law mu naught. Okay, this just means that their joint law, which we'll denote by Fn naught, is a tensor product. And then we ask, what is the limiting behavior as n goes to infinity of the law, joint law of the positions of the particles at time t? Well, if mu t is a solution of the mean field equation, is it true that Fnt, the joint law at time t, is essentially a tensor product? In other words, the particles are essentially IID, at least when n is very large. Okay, this doesn't actually make sense. It's not going to be true that the particles are independent for positive time. And this is because even if I start from independent initial data, I run time, the pairwise interactions create correlations, and that it destroys the independence. However, we might expect that the size of these correlations is small, particularly when n is very large. And more precisely, if we look at the marginals of the system, so say I fix a certain number of particles, k, to look at, and I take out all the other information in my system, that these marginals become independent or correspond to independent probability distributions when n is large. And this is exactly what propagation of chaos refers to. The asymptotic factorization of the marginals of my system and particle system, where the common factor is given by the solution in the mean field equation. So it is known that mean field convergence and propagation of chaos are closely related, even though they may look very different, at least at first glance. And in fact, they are equivalent in a qualitative sense. You know mean field convergence, then in fact you know propagation of chaos, vice versa. But in general, exchanging rates of convergence between the two is a trickier business. There's a closely related notion to propagation of chaos, which is that of generation of chaos, which is a term that I learned from Jani Lukarinen at Helsinki. So the idea now is that even when the initial law Fn naught is not chaotic. In other words, the particles are not independently, say, and identically distributed initially, one still has that their joint law becomes essentially chaotic when t is very large and n is very large, in some sense between the two. More precisely, if I look at the difference between the marginals in my n particle system and independent copies of the solution of the mean field equation, there are two sources of error. The first one is vanishing as n goes to infinity uniformly in time, while the second one is vanishing as time goes to infinity and only depends on the initial data. Yes?
Sorry, can I ask something? Just because it sounds interesting, but I have one. How is this limit now? Do you like increase the density, or is it going to like an infinite system size at kind of constant density? I haven't fully understood.
You've got the containing potential, right?
Yeah.
Yeah, so I'm not sure I understand the question. So,
well, I'm just thinking like in physics, let's say it makes a difference if you go.
So the mass here is, they're always probability measures, so it's normalized to 1.
No, mass allowed to escape to infinity, or is the density getting high? Because you have a fixed confining potential.
Sure.
I add n particles, the density is going to get higher.
So the density is going to 0 as n goes to, as space goes to infinity.
Space goes to infinity, but the density near 0, does that accumulate as n goes to infinity? What happens to the density in the localized region?
Yeah.
Well, you're going to have positive mass in that region. The density is
bounded as n goes to infinity.
My density is, well, for the purpose of theorems, I will assume that I have an L infinity density.
So number of particles is n, right?
Yes.
But volume that you can access, does the scale just the same as n?
I don't scale the volume. It's everything I say is the whole space.
Yeah, it's in a fixed confining parabolic domain.
Okay. Right. Sorry.
Interesting. It's an interesting question.
You have deep density then.
I think you're going to get high density, but it's not clear what order it will be.
But because also this force renormalization that you did, this I hadn't fully understood. So are the forces downscaled then relatively?
So I'm scaling the force so that for each particle it's of order 1.
Okay.
Then divides by n.
Okay, so it's not clear there how I wrote it, but if you express out the form of hn. So there's a nice picture or diagram you can draw in this case about what's happening both for the large n and large time behavior. So let's just consider this overdamp Langevin dynamics. So it's a gradient flow. That's because saying anything about the long time behavior for the Hamiltonian case is like impossible. What you would expect is that for fixed n, the joint law of the particles converges to the canonical Gibbs ensemble. Okay, this is the equilibrium description, which is just this object here we know from StatBack. So that's for finite n. What about in the limit as n goes to infinity? Well, we expect that the mean field density mu t should converge to what we call the thermal equilibrium measure, which I'll denote by mu beta. And this is the object, which is the minimizer amongst all probability measures, assuming it exists, of the macroscopic or mean field free energy, which is this object right here. Okay, so these mu are probability measures on my one particle phase space, which just say is RD. Of course, if V grows sufficiently fast in infinity, you can prove that this mean field free energy has a unique minimizer. That's actually not very hard. And it's uniquely characterized by the following relation right here, that the sum of the potential of the mean field density, the confinement, and the logarithm, the entropic term, is constant in all of RD. And okay, this is a diagram that I've drawn, the large n behavior up here, the large t behavior on these vertical arrows, and then of course what we're really interested in generation of chaos is this diagonal right here. In particular, how do n and t have to scale with each other? There's another question. So if we go beyond the mean field limit, propagation of chaos at next order. So what you have to understand is that the mean field limit in stats term is a law of large number of result. Okay, that's the proper analogy. And it describes the leading order behavior of this empirical measure, the first approximation. The next order behavior is captured by the fluctuation field, which is not properly normalized right here. It's just the difference of the empirical measure and the mean field equation. The question that we're interested in is what is the size of this fluctuation field? How does it scale with n? Which we'll denote by the reciprocal of sigma n. And if I properly normalize the fluctuation field, does it converge to a solution of some equation, some partial differential or stochastic partial differential equation? Can we characterize that solution? Is it Gaussian? And affirmatively answering this last question amounts to essentially proving a central limit theorem, okay, which, again, if you think back to your Stats 101 class, if you took one, this is the next result you learn after the law of large numbers. It's actually more interesting if a non-central limit theorem holds, that the fluctuations are not Gaussian, but often they tend to be. So these are the questions that we're interested in. I have just advertised a bunch of work that has been done, at least at the level of the mean field limit propagation of chaos. We don't have the time, and I don't have the wherewithal to go through all of this, and I'm probably forgetting lots of people, so if your name is not on here, don't yell at me afterwards. The point of this is to convince you that there's been a lot of research that has been done on this topic. And in fact, what I'm going to talk about in more detail now is a body of work in more recent years, so-called modulated energy and free energy techniques, which have developed specifically to study these Coulomb Riesz gases, okay? And have allowed us to obtain essentially state-of-the-art results. So with that, what is modulated energy? Well, it's this object right here. So what are we doing? Well, we're taking our empirical measure associated to some point configuration. We look at its difference with this mean field density mu, and we take the potential of that, okay? In other words, we're taking the energy of this difference. We have to make some small modification, which is important. Namely, this slash triangle means that I'm excluding the diagonal from this integration. And the reason I'm doing that is precisely because of these Dirac masses right here, okay? If I didn't exclude the diagonal, that would be a source of infinity. And this exclusion corresponds to removing the self-interaction, which I said at the beginning, we always have to take into account, excise if we want to get something which is finite. So I guess you could think of this as the total interaction of a system of n discrete charges at positions xi against a neutralizing background charge density mu, with the self-interaction removed. So this quantity first appeared, I guess, in the math world in work on the statistical mechanics of Coulomb Riesz gases by Sylvia and collaborators. And in that context, it arises as a next order energy. So there's a so-called splitting formula where you look at the n particle Hamiltonian and you subtract off the leading order macroscopic component of this. And what you get is precisely this modulated energy, using the characterization of the thermal equilibrium measure that I advertised a few slides ago. I guess for the physicists, this may look similar to what's called a jellium energy, or Riesz jellium. My understanding is that in the physics literature, this is usually refers to an infinite configuration of particles against a uniform background, so mu would be identically 1. So I avoid this terminology because this is not quite that. The case mu identically 1 in all of RD would not correspond to a probability measure, which I'm always assuming mu to be. So in the dynamics context, this was first used in work by Mattia Dwerings and then by Sylvia. And the key idea is that you want to establish what's called a Grand-Rolle relation for this quantity. So I take a solution of the n particle system, that's xnt. I take a solution of the mean field equation mu t. I plug both of these in to this modulated energy. I want to differentiate this in time. And I want to massage the right-hand side that I get after differentiating time into something which is controlled back by this guy right here. Because if I do that, I can obtain a closed estimate for the modulated energy in terms of the initial data at any time. Okay? So the idea of modulated energy or modulated energy techniques is actually fairly classical in math. The first time I saw the term modulated energy appear in a paper is work by Jan Brenier from over 2 decades ago. It also has strong similarities with what's known as the relative entropy method, which is classical for studying conservation laws and also been widely used for studying hydrodynamic limits. Why it works is it exploits what's called a weak-strong uniqueness principle for the limiting equation. Weak-strong uniqueness just means that, say I have some initial datum, And I have two notions of solution for an equation. One is a weak solution, which means that, say, it satisfies the equation in some integral form after doing integration by parts. The other is a strong solution, meaning it satisfies the equation in a pointwise or classical sense. What a weak, strong uniqueness principle says is that, in fact, these two notions of a solution have to coincide. Okay? The advantages of this method are that it's quantitative. There's no need for studying the microscopic dynamics. Its disadvantages are that it typically requires some regularity for or an a priori assumption on the limiting solution, but there's been some work in addressing that. So the first question you should ask is, why is this modulated energy a good quantity to consider in the first place? Why does it allow us, or why will it help us prove this mean field convergence that I said we're interested in? Well, to understand this, let's consider a simple example where G is just the Coulomb potential, which means that if I take minus Laplacian of G, I should just get a constant multiple of the Dirac. So if I take some test function, f, and I take its potential G, or its convolution, then okay, you can check that the energy of f can be rewritten in this form, okay, in terms of the gradient of the electric potential. And in math terms, this corresponds to the square of the h dot minus 1 Sobolev norm, homogeneous Sobolev norm. The issue is that I want to consider this quantity for a particular choice of f, namely the difference of an empirical measure and this reference mean field density mu. But this doesn't make sense. If I plug in such a choice of f in this expression, where dimension is greater than or equal to 2, I will get an infinite. Okay? Well, this is still the right idea. You just need to renormalize the computation. And what I mean by that is, well, let's again take the same quantity as before, except now let me take my point charges and let me smear them out a little bit at some length scale eta I. So instead of having charge that's supported at a point, I say have charge which is supported on a shell of some radius around the point. And again, I look at its electric potential. And what you can show is that, well, if these radii that I smear my charges at are small enough, namely that they're essentially of the order of the nearest neighbor distance between particles, then I can express this modulated energy as this renormalized energy functional. Okay, so this is the same quantity that I had before, except with h replaced by this regularized version. I have this term right here, which is subtracting off the self-interaction. And then I have this term right here, which you should think of as an error term. It vanishes as these eta I go to 0. Okay, so this is what's called in this business the electric reformulation. And it makes it clear that the modulated energy is a renormalized energy. And in fact, okay, I just did this for the Coulomb case, but you can extend this idea of renormalizing the energy through charge smearing to all of these log and Riesz interactions. So what this expresses is that the modulated energy is essentially a coercive quantity. Okay, I illustrated before this connection with the h dot minus 1 Sobolev norm. In math terms, this means that the modulated energy metrizes weak convergence. Okay, so if we can show this modulated energy vanishes, this will imply the convergence of the empirical measure to the solution of the mean field equation, which is what we're interested in. So how do you establish this Granville relation? Well, suppose for simplicity, we'll come back to the positive temperature case, that beta is equal to infinity. So we're 0 temperature. There's no noise, which I guess is a bit of sacrilege for this theme of this workshop. But I take, again, this solution of the n particle system, solution of the mean field equation, plug this into the modulated energy, differentiate in time. And it's a small computation that you will get exactly this expression right here, where ut is a vector field which only depends on the solution of the mean field equation. It does not depend on the n particle system. So suppose for a moment that we have a functional inequality, something that says that this expression is controlled in magnitude by something that depends on this vector field u, in a quantitative way, let's say, times the sum of the magnitude of the modulated energy at time t, and then plus some error term which is negligible as n goes to infinity. And I claim that if you have such an inequality, you're done. You have proven mean field convergence. And why is that? Well, you can take this, you can apply it to this right-hand side, and you can use what's known as Granville's lemma, which is guess, differential equations, basic lemma, and you would control the magnitude of the modulated energy at any time in terms of its initial value, and some error term which is negligible as n goes to infinity. There's this time-dependent factor right here, but what's important is that this expression, exponential, is finite for timescales, let's say, of order 1. And again, it only depends on the solution of the mean field equation through this vector field. So the question you should be asking yourself is, well, how would I ever show such a functional inequality? Not so obvious. So here's what you need to understand. Is that in the context of mean field limits, and also for studying fluctuations and beyond, it is essential to control quantities that correspond to differentiating this Fn along a transport field. And what do I mean by that? Well, take some vector field, take this map, which is just the identity plus linear transport in time, and displace your particles by this map, and also displace your probability measures by this map, pushing them forward. So if you do this, you differentiate n times, and then evaluate at n equals 0, t equals 0, computing the nth variation, you will get exactly this expression right here. And if you take n equals 1 and compare this to this guy right here, this is exactly the first variation of the modulated energy along this particular transport field ut. So this is really a harmonic analysis problem. It has nothing to do with mean field limits. You want to prove functional inequalities that say that the right-hand sides, the nth variations of the modulated energy, are controlled by something which depends quantitatively on the transport v, times the sum of the modulated energy, and then plus some error term which is negligible as n goes to infinity. Because as I said before, once you have this, you're done. So there's two perspectives, or at least two perspectives, on proving these functional inequalities. The first perspective originates in some work by Thomas Leblay and Sylvia several years ago. And the idea is to interpret this expression for the first variation in terms of a stress energy tensor structure. So to illustrate this, consider the Coulomb case. So again, I look at this electric potential of the difference between the empirical measure and this reference mean field density, which I'll denote by Hn. And using this, it's again a small computation that you can rewrite this expression, this double integral, as a single integral of the vector field tested or inner product with the divergence of the stress energy tensor associated to Hn, which is this object right here. So what's good about this is that since I have a divergence, I can integrate it by parts, and I can throw this off onto the vector field, which is as regular as I assume it to be. And then if I do that, I can then use the Cauchy-Schwarz inequality. I can just bound this gradient of v in the simplest way by L infinity. And what I'm left with is the square L of the gradient of my electric potential difference in L2. That's good because formally, this is exactly the Coulomb energy of the difference between this empirical measure and the reference mean field density. The problem is that this computation is not valid, or it's not rigorous. And this is precisely because that for this definition of Hn, the L2 norm is infinite. The singularity of the Dirac masses leads to this infinity. However, this is still the right reasoning. You just need to implement it after a renormalization. And again, the idea is to take your charges and smear them out a little bit so you get something which is more regular. And you can apply this reasoning to this smeared out or regularized electric potential, Hn eta, where again, you have to choose your smearing radii, say roughly of the order of the nearest neighbor distance between particles, which is, if you think about n particles in a box of size 1, the typical interparticle distance is like n to the minus 1 over d. And OK, well, you make this replacement. You do this stress energy tensor argument with this Hn eta. Works. The issue, or what you still have to do, is then you have to appropriately choose your smearing radii and then estimate the error that you've introduced by making this replacement, this regularization. You can do that through a separate argument, which I don't have time to go into. And it works. The stress tensor approach is quite elegant. It's very low tech. All we're using here is integration by parts. And it's based on purely local arguments, which means that it allows you to take into consideration the contribution to the energy from particles in a fixed region of space. It's rigid, though, in the sense that if I wanted to consider potentials that didn't belong to this Riesz family exactly, some perturbation of this, it's not clear how you would implement this. The second perspective is what I'll call the commutator perspective, and it originates in work of myself from several years ago, and then was generalized substantially in work with Hung Nguyen and Sylvia. And the idea is as follows. So let's denote this difference between the empirical measure and the mean field density by F to compactify the notation. You can take this expression for the first variation. You can, again, rewrite it as an integral, a single integral, just by using convolutions. And then you can take this expression and you can write in the following form. So what is going on here? This bracket is a commutator between two operators. The first operator is multiplication by the components of the vector field. And the second is the pseudo-differential or Fourier multiplier. Minus this delta is to this d minus s over 2 is the fractional Laplacian, which you can just define spectrally in all of our d in terms of its Fourier transform. And so I'm taking the commutator between these two operators, and I'm looking at the associated quadratic form in L2 between this object. So punchline, the first variation is the quadratic form associated to a commutator. And you can similarly formulate the higher order variations in terms of iterated commutators. So the idea, or what's good about this, is that there's a very large literature in harmonic analysis about proving estimates for commutators, particularly in L2 spaces. For instance, the Coulomb case corresponds to what are known as Calderon decommutators. And what we would like to do is we'd like to be able to apply these estimates. We have the same problem as before, is that this f that we're considering is too singular to directly apply it. But again, you can do some sort of renormalization. You can regularize this object, apply some, say, off-the-shelf estimate to this regularized object, and then separately estimate the error that you've introduced by the regularization. And it works. And in fact, you can do this for these Riesz families, but you can also do it for general interaction potentials that have, say, a similar Riesz-type structure, and even beyond that. So there are some important questions here, which you may have occurred to you, which is, OK, I said that we're interested in this following functional inequality. We want to control the first variation along a transport back in terms of the modulated energy, plus some error term, which is negligible as the number of particles tends to infinity. But an important question is, how small can you make this error? How large can alpha be? Larger alpha means smaller error, better rate of convergence. There's a limit. Namely, the best you can hope for is that both of these terms here scale essentially of the same order as n goes to infinity. And we'll say this functional inequality is sharp if this is the case. So by counting only nearest neighbors, which, as I mentioned before, have a typical distance of n to minus 1 over d, you expect that this modulated energy is typically of the order n to the s over d minus 1. Remember, s is the parameter indexing the Riesz interaction. And in fact, you can show that this modulated energy is bounded from below by a negative multiple of n to the s over d minus 1. This is a theorem. And in fact, it's known that this lower bound is achieved. If I look at minimizers of my n particle energy, and I compare this to the minimizer of the mean field energy, they will have exactly that order, minus some constant n to the s over d minus 1. And in certain cases, you know the constant. OK, so punchline of this is that the optimal exponent that we should expect up here is alpha equals 1 minus s over d. But this originally had only been shown in the Coulomb case, and work by Thomas and Sylvia, and then later another proof by myself. The final comment, which I'll just flash through, is you want to be another important aspect is the localizability of such estimates, which I kind of alluded to before. Namely, you want to take into account the contribution to the energy from particles in a fixed region of space. You can introduce localized versions of the modulated energy. So omega is some subdomain of all of our D. And again, you would ask the same question. Can I control the first variation in terms of a localized modulated energy with some air, which again is only depending on particles in this fixed region of space? So what can we actually say about all these questions? Over the last few years, we have proven the sharp commutator estimate in all log Riesz cases. So the Coulomb, super Coulomb case was done first, and some work with Sylvia from a few years ago. It took a while to actually write the paper. And then most recently, we also treated the sub-Coulomb case with Elias and Sylvia. And an immediate application of these estimates is that we have the optimal n to the s over d minus 1 rate of convergence for the mean field limit measured in this modulated energy distance. Previously, this optimal rate was only known in the Coulomb case. And in fact, there's another application which I don't have time to go into, which has to do with the scaling, optimal scaling, what's known as supercritical mean field limits. So this 1 over n is replaced by, say, 1 over squared n, or something which decays less fast. So maybe I'll just say that the proofs use both perspectives. The stress energy tensor and commutator perspective are actually in two sides of the same coin. They're in duality with each other, as we learned. And in both cases, okay, so the proofs are still they're rather different in the end. But in both cases, the idea is the same, is that you want to prove estimates first when you have some regular test function, so not this difference of the empirical measure in the mean field density. And then you want to apply those estimates to these regularized versions and then separately estimate the error, the renormalization step. Okay, so it's really a two-step process. Maybe skip over this part. These are just a few words about the actual proof. Skip that. So positive temperature. What I illustrated before was the computation when beta is equal to infinity. Many of the ideas, though, carry over. And the most important one is the commutator estimate. That's really the workhorse of all of this business. So you can just take this modulated energy approach and directly generalize it to the case where you have noise, which persists in the limit. And we did this with Sylvia. And all you do is, okay, instead of looking at the modulated energy, you look at its expected magnitude, okay, where you now have randomness in it. This works if the interaction is not too singular, namely in all the sub-Coulomb cases for either conservative or gradient dynamics. And this is a purely pathwise result. It doesn't require any randomness of the initial data. The randomness is only in the dynamics. And in fact, by exploiting convergence or relaxation of the mean field density to equilibrium, you can even prove estimates which are uniform in time, so that exponential factor in time that you saw before can be bounded by something which is of order 1. But you'll notice here that if S is strictly less than d minus 2, this is not covering the Coulomb case, okay, which is most physically relevant. And the reason it doesn't work when S is greater than or equal to d minus 2 is not very deep. It's because G, the interaction potential, is superharmonic in math terms in the sub-Coulomb case, meaning that if in this regime, the Laplacian of G is not a non-positive locally integrable function. And why that's relevant is that, well, if you try to do the same computations, but when you have noise, you know what Ito's formula is, you'll get a term that corresponds to exactly the Ito correction compared to the usual chain rule. Now, in this regime, S is strictly less than d minus 2, this guy right here is essentially non-positive up to some negligible error, and so I just ignore it. But of course, this breaks down exactly when S is equal to d minus 2. What's missing is that when you have noise, the modulated energy is not really the right quantity you should consider. You're missing an entropic term, which removes this pathological term. And this leads us to what's known as modulated free energy, which is a beautiful idea of Riesz, Jaban, Wang. And okay, I just take my modulated energies before, and I add to it an entropy term, an entropic term. So what's going on here? Well, Fn is the distribution of my particles, my n particles. I view them as randomly distributed with this law Fn. Mu is, again, this mean field reference density. This first term right here is just the relative entropy, or KL divergence, between this joint n particle law and n independent copies of the mean field law. And I normalize this by the temperature. And this second term right here is just the average of the modulated energy, where I'm averaging out the randomness. So this object is very well suited to studying the over-Longevin dynamics, so gradient flows. In all Riesz cases, it is not well suited to studying Hamiltonian dynamics. The reason why it works, is that there's sort of a stat mech interpretation of this, which is that given a reference probability measure mu on my one particle phase space, I can define what's known, or what we call this modulated Gibbs measure. So this is just, instead of the usual energy functional, I now have the modulated energy and the exponential. My reference measure is n copies of the mean field density. And then I have my partition function, so I get something which is genuinely a probability measure on n copies of my phase space, one-dimensional phase space. So using this modulated Gibbs measure, you can rewrite this modulated free energy as a relative entropy of the joint law of the particles, Fn, relative to this modulated Gibbs measure associated to mu. And then there's some air term, which is like a free energy. So modulated free energy is really just another relative entropy. So what's good about this for gradient dynamics is that this modulated free energy satisfies a dissipation inequality. In all of gradient flows, in order to do something, you need a dissipation relation. I can control the time derivative of my modulated free energy in terms of this guy right here, which is relative Fisher information between the joint law of the n particle system and this modulated Gibbs measure, where mu t is the mean field flow. This is good because I would expect this to provide some source of dissipation or diffusion, say through a log Sobolev inequality. And again, this second term right here, this laser is not working very well, is exactly this commutator expression that we saw before, the first variation, except now that it's averaged over the law of the particles, Fn. And importantly, again, the vector field, similar as before, except we've gained an entropic term coming from the temperature. Why I've rewritten it in the second form right here is because this makes it clear that you should expect some decay of ut for large t. Because as I mentioned before, mu t should converge to mu beta, so this term should vanish, and similarly, this guy should vanish as well. This is important for proving uniform in time estimates. Right, so you can close this relation using Gronwall's lemma precisely by using a commutator estimate as before. Nothing changes. If you want, you can just discard this relative Fisher information on the right-hand side. It's non-positive. Turns out you shouldn't do that, because if you want to establish, say, these generation of chaos results, this is the term that you need to use. And you can also do this even uniformly in time, get estimates which are uniform in time. So this modulated free energy was first done by Breschabon Wang, and then the uniform in time extension was some more recent work with Antonon and Sylvia. So this is the positive temperature case. It's very similar to the zero temperature case. As I mentioned before, the workhorse is the commutator estimate. And to summarize, modulated free energy and commutator estimates have allowed us to prove mean field limits and propagation of chaos. So I didn't dive into this, but once you have these rates of convergence for the modulated energy, these also imply sort of a standard argument, rates of convergence for propagation of chaos. We have these for all log Riesz interactions with fixed or even vanishing temperature for both conservative and dissipative dynamics. The sharp error, which I said is n to the s over d minus 1, has been achieved. And you can even obtain rates of convergence that are uniform in time, at least in cases where there's a dissipative or diffusive effect, either from the noise or from the dynamic itself. You could have a nonlinear source of diffusion. I should also mention that you could, in fact, do this even for interactions that are attractive and mildly singular. This is relevant, for instance, in dimension 2. This corresponds to the so-called Potler-Kelly-Seeger model of chemotaxis. So I don't know how I'm doing on time. I imagine not well. OK, so I'll wrap it up. So I don't have time to go through the business on fluctuations. Maybe I will actually just say one word, which I think is interesting. And I haven't seen this before in the physics literature. So given this, you may have some insight into this. So I introduced these modulated Gibbs measures as before. And these actually include the canonical Gibbs ensemble. If you just take mu to be the thermal equilibrium measure and you plug this in, you will recover exactly the Gibbs ensemble. There are two extremes to this regime. Beta equals 0 is infinite temperature. And you can see that this Qn then just becomes n independent copies of mu. Beta equals infinity is the 0 temperature, which corresponds to the ground state. At least formally, Q becomes a probability measure which is supported on the set of minimizers of this modulated energy, assuming such an object exists. So for instance, if you knew you had a unique minimizer, it would just be a Dirac-Moss at that particular minimizer. So why I mention this is a key question that you're interested in that I mentioned before is what is the size of fluctuations? How small or large can they be, depending on the temperature? And you can generate different scalings of fluctuations as you tune this beta n by considering points which are distributed according to these modulated Gibbs measures. So I have a conjecture, which I have not seen even in the physics literature before, where now you suppose these points are distributed according to this Qn, and I allow the temperature to scale with n, beta n. So I believe that the fluctuations have normalization size sigma n, which is given by this expression right here. So I take the maximum of square root beta n, n square root n. So if beta n is becoming very large, the temperature is going to 0, then this first guy prevails. So square root beta n is the normalization. On the other hand, at very high temperature, the size should just be square root n, or 1 over square root n, the size, which corresponds exactly to the size of fluctuations for IID particles. This should at least hold when this relation right here is satisfied. So at low, very low temperature, it should break down. The punchline of this is that order, i.e. lowering the temperature, should create smaller fluctuations. This is actually known in certain cases that if you take smaller beta, you will have fluctuations which are much smaller than 1 over square root n. They could be like 1 over n. I can prove this conjecture using Stein's method in a certain sub-regime when this holds. And you can think of this as a high temperature result for reasons I don't have time to go into. The other observation is that square root n is exactly the normalization for IID particles in the classical CLT. And this says that when beta n is of order 1, at least, this is not really that different than the IID case, which for me corresponds to complete disorder. And again, it's clear that there has to be, to use an overloaded term, some phase transition somewhere, depending on the scaling of beta n. This square root beta n normalization cannot hold all the way down to 0 temperature, the ground state. Otherwise, this would imply that the ground state fluctuation was 0, which is, we know, not to be true. So if you have any insight into this conjecture, in particular physical insignificance, I'd be very interested to talk more. And with that, I will stop and thank you for your attention.
Okay, thank you very much.